Welcome. You've arrived here at the end of your day, carrying with you whatever weight the hours have brought. Let it rest now. Let your shoulders soften, your breath deepen, and your thoughts begin to slow, like leaves settling on still water. Tonight, you're going to travel somewhere both impossibly distant and intimately close. You're going to drift through the Milky Way, the great spiral of stars that holds our sun, our world, and every human story that has ever been told. This journey requires nothing of you except rest. There are no tests waiting, no facts to memorize, no urgency at all. Just wonder, moving at the pace of your breathing. The galaxy is always there, turning slowly above you even when daylight hides it. Right now, as you lie here, you're already traveling through it at hundreds of kilometers every second, though you feel only stillness. Tonight, we'll explore this river of light together, not with the bright curiosity of morning, but with the soft, wandering attention that comes just before sleep. We'll visit places where stars are born and where they die, where matter bends space and time flows differently, where light has been traveling for thousands of years just to reach your eyes. You don't need to remember everything. In fact, you don't need to remember anything at all. Let the words wash over you like gentle waves. Some will catch your attention, painting pictures behind your closed eyes. Others will simply carry you deeper into rest. Both are exactly right. So settle in, adjust your pillow one last time. Let your breathing find its own rhythm, slow and easy. The galaxy is patient. It has been turning for billions of years, and it will wait for you to arrive in your own time. Imagine for a moment that you could step outside not just your room, but outside the very fabric of the world. Imagine rising up through the atmosphere, past the thin blue shell that holds all weather, all clouds, all breath. You drift beyond where airplanes fly, beyond where space begins, until Earth becomes a sphere of blue and white and green below you. From here, if you could wait and watch, you would see the sun as just another star. And if you could travel further still, moving not through space alone, but through perspective itself, you would begin to see something magnificent. All around you, in every direction, stars emerge from darkness. Not the handful visible from your backyard, but billions upon billions, arranged in a pattern so vast that human eyes took millennia to even begin to understand it. You're about to explore this pattern, this structure, this island of matter and light and mystery called the Milky Way. The name itself is ancient, whispered in different languages across different lands. The Greeks saw spilled milk from a goddess. The Romans called it the Via Lactea, the road of milk. Other cultures saw a river, a path, a bridge between worlds. They were all describing the same luminous band that arcs across the night sky on clear, dark evenings. That foggy stream of light that looks almost close enough to touch. But what they saw was only a hint, a fraction, a single cross-section of something far more beautiful and strange. Because you, right now, are not looking at the Milky Way from outside. You're inside it. You've always been inside it. Every human who has ever lived, every thought that has ever been thought, every breath ever taken has happened deep within this spiral of stars. When you look up at that band of light, you're seeing your home from the inside, looking through layers and layers of stars toward the galaxy's crowded heart. Let's begin where all things begin, in time so deep that numbers almost lose their meaning. Imagine going backward through history, past yesterday, past your childhood, past the lives of your grandparents and their grandparents. Keep going, past the building of ancient cities, past the first farmers, past the cave painters who drew by firelight. Further still, past the evolution of our species, past the dinosaurs, past the first forests and the first fish, back to a time when Earth was molten and young. We've barely started. Keep traveling backward through time. The solar system dissolves. The sun has not yet formed. There is only a cloud here, a nebula, rich with dust and gas, slowly collapsing under its own gravity. But we don't stop here either. We go further and further through billions of years, until the Milky Way itself begins to unform, to separate into smaller pieces, into the scattered clouds and dwarf galaxies that will eventually merge and spiral into the structure that now holds us. About 13 billion years ago, give or take, in the wake of the universe's beginning, the first building blocks of our galaxy came together. Not all at once, not from a single cloud, but gradually, chaotically, through collision and accumulation and the patient, invisible pull of gravity. Small galaxies merged, gas clouds collapsed, the first stars ignited, lived briefly and died, seeding space with heavier elements: iron, carbon, oxygen. The raw materials that would one day form planets and trees, and the person listening to these words. The early Milky Way looked nothing like it does now. It was smaller, more chaotic, less organized, but already within that primordial structure, the fundamental forces were at work. Gravity gathering matter, angular momentum setting things spinning, and something else, something we still don't fully understand, something that doesn't emit light or heat, but shapes the galaxy through pure gravitational influence alone. Dark matter. 5 times more abundant than ordinary matter, this invisible substance forms a halo around the galaxy, extending far beyond the visible stars. We cannot see it directly. It does not interact with light, but we know it's there because of how it pulls, how it shapes the orbits of stars. how it holds the galaxy together despite the tremendous speeds at which everything moves. The stars you see are just the visible tip of something much larger, like fireflies illuminating the shape of an invisible sphere. Imagine the galaxy forming like a whirlpool in slow motion. As matter fell inward, drawn by gravity, it began to rotate, not rigidly like a solid disk, but differentially, with the inner regions spinning faster than the outer ones. Over hundreds of millions of years, this rotation stretched and organized the material into the flat, spiral structure we see today.
But why a spiral? Why do galaxies form these elegant, sweeping arms rather than remaining as simple disks? The answer is subtle, beautiful, and reveals something profound about how patterns emerge in nature. The spiral arms are not fixed structures. They're not solid, permanent features with the same stars always occupying the same positions. Instead, they're density waves, regions where stars and gas temporarily bunch together as they orbit, the way cars bunch up in slow-moving traffic, even though individual cars are constantly entering and leaving the jam. Picture it this way. Every star in the galaxy follows its own elliptical orbit around the galactic center. These orbits overlap and interact in complex ways. Where orbits naturally bunch together, you get a region of higher density. More stars, more gas, more dust. This denser region has stronger gravity, which attracts even more material. As stars enter this density wave, they slow down slightly, bunch together, then speed up again as they leave. The wave itself rotates around the galaxy more slowly than the stars do, creating a persistent, beautiful spiral pattern. And in these spiral arms, something remarkable happens. The extra density compresses clouds of gas and dust. When these clouds compress enough, they collapse under their own gravity. Temperatures rise, pressure builds, and finally, gloriously, fusion ignites in their cores. New stars are born. This is why the spiral arms shine brighter than the regions between them. They glow with the light of stellar nurseries, vast regions where thousands of stars are forming simultaneously, wrapped in the glowing nebulae of their birth. The most massive of these newborn stars burn brilliant blue-white, living fast and dying young, never surviving long enough to drift out of the spiral arm where they formed. They mark the arms like lights along a highway, making the pattern visible across intergalactic space. The Milky Way has several major spiral arms, though astronomers debate the exact number and structure. There's the Perseus arm, the Scutum Centaurus arm, the Norma arm, and others. These arms wrap around the galaxy, trailing behind like water streaming from a spinning sprinkler. Our sun, our solar system, sits in a smaller feature called the Orion Spur, a minor arm connecting two major ones. We're about halfway out from the center, roughly 26,000 light-years from the galactic core, in a relatively quiet neighborhood between the bright, bustling lanes of the major spiral arms. But the galaxy is not perfectly symmetrical. It's not a simple spiral. At its heart, there's a structure that surprised astronomers when they finally mapped it clearly. A bar. Not spiral, but elongated, stretching across the galactic center like a thick rod of stars. This central bar rotates as a single cohesive structure, and it plays a crucial role in the galaxy's dynamics, funneling gas inward toward the center, triggering star formation, shaping the orbits of everything around it. Think of the Milky Way now in your mind's eye, not as a simple spiral, but a barred spiral, a majestic structure with sweeping arms trailing from the ends of a central bar, all of it slowly rotating, all of it breathing with the birth and death of stars, and all of it embedded in that vast, invisible halo of dark matter, like a jewel set in a crown we cannot see. The galaxy is approximately 100,000 light-years across. Let that distance settle in your mind for a moment, though it's almost too large to truly comprehend. Light, which could circle Earth 7.5 times in a single second, takes 100,000 years to cross from one edge of the galaxy to the other. If you sent a message at light speed from one side to the other, the reply would return after 200,000 years. Entire civilizations could rise and fall in the time it takes information to cross this structure. And yet, on cosmic scales, the Milky Way is not particularly large. It's a medium-sized spiral galaxy, neither giant nor dwarf. There are galaxies out there 100 times its diameter, and galaxies so small you could fit hundreds of them inside the Milky Way's volume. We're part of what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity, all slowly dancing around a common center of mass. Our nearest large neighbor is Andromeda, the great spiral galaxy visible to the naked eye on dark autumn nights in the northern hemisphere. Andromeda is about the same size as the Milky Way, perhaps slightly larger, and it lies about 2.5 million light-years away. That might sound impossibly distant, but in cosmic terms, it's practically next door. And Andromeda is getting closer. Right now, even as you rest here, the Milky Way and Andromeda are approaching each other at about 110 kilometers per second. In roughly 4 billion years, give or take, they will collide. Not in the sense of stars actually hitting each other, space is far too empty for that, but the two galaxies will merge, their spiral structures disrupted and reformed, their gas clouds colliding and triggering immense waves of star formation until eventually they settle into a single, larger elliptical galaxy that astronomers have playfully nicknamed Milkomeda.
But that collision is still billions of years away. For now, the Milky Way spins peacefully in its corner of the universe, home to somewhere between 100 billion and 400 billion stars, depending on how you count and what you include. Each of those stars is a sun, potentially with its own family of planets, its own story of formation and evolution. Some are larger than our sun, burning fierce and fast. Others are smaller, dimmer, more patient, destined to burn steadily for trillions of years, long after stars like our sun have exhausted their fuel and faded. Let's drift inward now, toward the heart of the galaxy, toward the place where everything began and where the most extreme physics plays out. Imagine traveling from our position in the Orion Spur, moving through the spiral arms, passing clouds of glowing hydrogen, passing stellar nurseries wrapped in dust, passing regions where massive stars have exploded and left behind their shredded remains. As you move inward, the density of stars increases. Space becomes more crowded. The night sky, if you could see it from a planet closer to the galactic center, would blaze with thousands of stars bright enough to cast shadows, a sky that never truly darkens. The average distance between stars shrinks from light years to mere light months, then light weeks. And at the very center, at the point around which everything orbits, There is something both invisible and overwhelmingly massive. A supermassive black hole, given the name Sagittarius A star, pronounced Sagittarius A star. This object contains approximately 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. It is not a star. It is not made of matter in any conventional sense. It is a place where gravity has become so intense that it has torn a hole in the fabric of space-time itself, a region from which not even light can escape once it crosses the boundary called the event horizon. You might expect such an object to be constantly consuming everything around it, glowing with the light of infalling matter. But Sagittarius A1 is surprisingly quiet. It's not actively feeding. The space immediately around it is relatively empty. Most of the time it just sits there, dark and patient, making its presence known only through its gravitational influence on the stars that orbit nearby. And what orbits it has. Astronomers have watched stars loop around Sagittarius A1 in elliptical paths, some completing their orbits in just a few years, reaching speeds of several percent the speed of light at their closest approach. These stars provide some of the strongest evidence that the black hole is really there. They're moving so fast, in such tight orbits, that only an immense concentration of mass in a tiny volume could explain their motion. By tracking these stellar orbits with incredible precision, astronomers have mapped the position and mass of the black hole to remarkable accuracy, even though they cannot see the object itself. Sometimes material does fall toward Sagittarius A1, gas, dust, maybe occasionally something larger. When this happens, the material heats up as it spirals inward, reaching temperatures of millions of degrees, glowing in X-rays and radio waves, before finally vanishing beyond the event horizon. These brief flares of activity allow astronomers to study the region right at the edge of the black hole, where space and time become severely warped, where the rules of physics push toward their most extreme limits. But even this monster is small compared to the central black holes in other galaxies. The one at the heart of the galaxy M87, for instance, contains more than 6 billion solar masses. That galaxy recently made headlines when astronomers managed to capture the first direct image of a black hole's shadow, the dark circle where light cannot escape, silhouetted against the glowing material swirling around it. Sagittarius A1 is harder to image because it's much more variable, flickering on timescales of minutes as material swirls around it. Surrounding the central black hole is the galactic bulge, a dense, elliptical swarm of stars that predates most of the galaxy's disk. These are old stars, ancient, metal-poor stars that formed early in the galaxy's history. The bulge has a strange shape when viewed edge-on. It's not spherical, but rather peanut-shaped or boxy, a structure that results from the way the central bar twists and buckles the distribution of stars in the inner galaxy. Moving outward from the bulge, you enter the disk, where most of the galaxy's mass in stars and gas resides. This disk is thin, relatively speaking, only about 1,000 light-years thick, but tens of thousands of light-years across. Within this disk, the spiral arms wind, and within the arms, the cycle of stellar birth and death plays out endlessly. Star formation is not uniform throughout the galaxy. It clusters in the spiral arms and the densest molecular clouds, where gravity can overcome the internal pressure of the gas and trigger collapse. These clouds are vast, dark, and cold, barely above absolute zero. They're made mostly of hydrogen molecules, along with traces of other compounds, dust, water ice, organic molecules, all the raw ingredients for stars and planets. When a cloud collapses, it fragments into smaller pieces, each piece collapsing further, heating up, spinning faster. Eventually, many of these fragments become stars. The largest ones burn hot and blue, flooding space with ultraviolet light, ionizing the surrounding gas, and making it glow in shades of red and pink. These regions, called H2 regions, are some of the most beautiful objects in the galaxy. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one such region, a stellar nursery relatively close to us, only about 1,400 light-years away. The massive stars in these nurseries live fast. They might burn for only a few million years before exhausting their fuel. When they die spectacularly, exploding as supernovae, events so bright they can briefly outshine entire galaxies. These explosions serve multiple purposes. They disperse heavy elements, forged in the star's core and in the explosion itself, enriching the interstellar medium with carbon, oxygen, iron, gold, all the elements heavier than hydrogen and helium. They also send shockwaves rippling through nearby gas clouds, compressing them, sometimes triggering new rounds of star formation. But that collision is still billions of years away. For now, the Milky Way spins peacefully in its corner of the universe, home to somewhere between 100 billion and 400 billion stars, depending on how you count and what you include. Each of those stars is a sun, potentially with its own family of planets, its own story of formation and evolution. Some are larger than our sun, burning fierce and fast. Others are smaller, dimmer, more patient, destined to burn steadily for trillions of years, long after stars like our sun have exhausted their fuel and faded. Let's drift inward now, toward the heart of the galaxy, toward the place where everything began and where the most extreme physics plays out. Imagine traveling from our position in the Orion Spur, moving through the spiral arms, passing clouds of glowing hydrogen, passing stellar nurseries wrapped in dust, passing regions where massive stars have exploded and left behind their shredded remains. As you move inward, the density of stars increases. Space becomes more crowded. The night sky, if you could see it from a planet closer to the galactic center, would blaze with thousands of stars bright enough to cast shadows, a sky that never truly darkens. The average distance between stars shrinks from light years to mere light months, then light weeks. And at the very center, at the point around which everything orbits, there is something both invisible and overwhelmingly massive. A supermassive black hole, given the name Sagittarius A star, pronounced Sagittarius A star. This object contains approximately 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. It is not a star. It is not made of matter in any conventional sense. It is a place where gravity has become so intense that it has torn a hole in the fabric of space-time itself, a region from which not even light can escape once it crosses the boundary called the event horizon. You might expect such an object to be constantly consuming everything around it, glowing with the light of infalling matter. But Sagittarius A1 is surprisingly quiet. It's not actively feeding. The space immediately around it is relatively empty. Most of the time, it just sits there, dark and patient, making its presence known only through its gravitational influence on the stars that orbit nearby. And what orbits it has? Astronomers have watched stars loop around Sagittarius A1 in elliptical paths, some completing their orbits in just a few years, reaching speeds of several percent the speed of light at their closest approach. These stars provide some of the strongest evidence that the black hole is really there. They're moving so fast, in such tight orbits, that only an immense concentration of mass in a tiny volume could explain their motion. By tracking these stellar orbits with incredible precision, astronomers have mapped the position and mass of the black hole to remarkable accuracy, even though they cannot see the object itself. Sometimes material does fall toward Sagittarius A1, gas, dust, maybe occasionally something larger. When this happens, the material heats up as it spirals inward, reaching temperatures of millions of degrees, glowing in X-rays and radio waves, before finally vanishing beyond the event horizon. These brief flares of activity allow astronomers to study the region right at the edge of the black hole, where space and time become severely warped, where the rules of physics push toward their most extreme limits. But even this monster is small compared to the central black holes in other galaxies. The one at the heart of the galaxy M87, for instance, contains more than 6 billion solar masses. That galaxy recently made headlines when astronomers managed to capture the first direct image of a black hole's shadow, the dark circle where light cannot escape, silhouetted against the glowing material swirling around it. Sagittarius A1 is harder to image because it's much more variable, flickering on timescales of minutes as material swirls around it. Surrounding the central black hole is the galactic bulge, a dense, elliptical swarm of stars that predates most of the galaxy's disk. These are old stars, ancient, metal-poor stars that formed early in the galaxy's history. The bulge has a strange shape when viewed edge-on. It's not spherical, but rather peanut-shaped or boxy, a structure that results from the way the central bar twists and buckles the distribution of stars in the inner galaxy. Moving outward from the bulge, you enter the disk, where most of the galaxy's mass in stars and gas resides. This disk is thin, relatively speaking, only about 1,000 light-years thick, but tens of thousands of light-years across. Within this disk, the spiral arms wind, and within the arms, the cycle of stellar birth and death plays out endlessly. Star formation is not uniform throughout the galaxy. It clusters in the spiral arms and the densest molecular clouds, where gravity can overcome the internal pressure of the gas and trigger collapse. These clouds are vast, dark, and cold, barely above absolute zero. They're made mostly of hydrogen molecules, along with traces of other compounds, dust, water ice, organic molecules, all the raw ingredients for stars and planets. When a cloud collapses, it fragments into smaller pieces, each piece collapsing further, heating up, spinning faster. Eventually, many of these fragments become stars. The largest ones burn hot and blue, flooding space with ultraviolet light, ionizing the surrounding gas and making it glow in shades of red and pink. These regions, called H2 regions, are some of the most beautiful objects in the galaxy. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one such region, a stellar nursery relatively close to us, only about 1,400 light-years away. The massive stars in these nurseries live fast. They might burn for only a few million years before exhausting their fuel. When they die spectacularly, exploding as supernovae, events so bright they can briefly outshine entire galaxies. These explosions serve multiple purposes. They disperse heavy elements, forged in the star's core and in the explosion itself, enriching the interstellar medium with carbon, oxygen, iron, gold, all the elements heavier than hydrogen and helium. They also send shockwaves rippling through nearby gas clouds, compressing them sometimes triggering new rounds of star formation. Every atom of carbon in your body, every atom of iron in your blood was created inside a star and scattered into space by a supernova or stellar wind billions of years ago, before the sun even existed. You are made of stardust, quite literally. The calcium in your bones, the oxygen you breathe, the gold in any jewelry you wear, all of it was forged in stellar furnaces and dispersed through the galaxy in violent deaths that made new life possible. This process of stellar birth, life, death, and recycling has been going on for billions of years, gradually enriching the galaxy with heavier elements. The oldest stars, formed early in the galaxy's history, contain almost no heavy elements. They're made of nearly pure hydrogen and helium, the primordial elements forged in the Big Bang. These ancient stars are called metal-poor in astronomical terms, where anything heavier than helium counts as a metal. As generations of stars have lived and died, each new generation has incorporated more of these heavy elements, becoming more metal-rich. Our Sun is a third-generation star, perhaps even later. It contains about 2% heavy elements, enough to form rocky planets, enough to make life possible. Earth itself is a testament to stellar death, a ball of iron and rock and water that could not exist without the element-forging furnaces of long-dead stars. The galaxy is not static. It's not a fixed structure frozen in time. It's dynamic, evolving, shaped by ongoing processes that play out over millions and billions of years. Stars are constantly forming and dying. Gas is constantly being recycled, and the galaxy itself is constantly interacting with its environment, pulling in smaller galaxies, stirring its own structure through internal dynamics. One of the most fascinating discoveries in recent decades has been the detection of stellar streams, long, thin trails of stars stretching across the sky. These streams are the remnants of dwarf galaxies that ventured too close to the Milky Way and were torn apart by tidal forces, their stars stripped away and strung out in long arcs that wrap around the galaxy multiple times. The Sagittarius dwarf elliptical galaxy is currently in the process of being consumed this way, its stars streaming through the Milky Way's disk, some of them passing right through our neighborhood. This is galactic cannibalism, a reminder that the Milky Way has not always been the same size. It has grown through mergers, through the accretion of smaller galaxies, and it continues to grow today. The dwarf galaxies of the local group, the dozens of small satellite galaxies orbiting the Milky Way, are all at risk. Some will eventually fall in and be absorbed. Others might survive, orbiting indefinitely in the galaxy's outskirts. This process of hierarchical assembly, small structures merging to form larger ones, is fundamental to how galaxies grow and evolve. By studying these stellar streams, astronomers can reconstruct the Milky Way's history, determining which dwarf galaxies were consumed and when, mapping the galaxy's growth over billions of years. It's like archaeology, But instead of digging through layers of soil, they're analyzing the motions and compositions of stars, reading the galaxy's history written in light. The Milky Way is also not perfectly flat. The disk has a warp, a bend that causes the outer regions to tilt up on one side and down on the other, like a record that someone sat on. The cause of this warp is still debated. It might result from interactions with satellite galaxies, or from the distribution of dark matter, or from past collisions. Whatever the cause, it means the galaxy's structure is more complex than the simple, flat spiral you might imagine. There's also asymmetry. One side of the galaxy appears slightly denser than the other. The spiral arms are not perfectly uniform. The bar at the center is not precisely aligned with anything in particular. All of this complexity reflects the galaxy's history, the countless interactions and events that have shaped it over billions of years. Let's talk about time for a moment, because time in a galaxy moves differently than time in a human life. You orbit the sun once per year. Earth completes its circuit, the seasons cycle, and a year passes. But the sun also orbits the galactic center, completing one full circuit approximately 220 to 250 million years. This is sometimes called a galactic year or cosmic year, though the term is informal. Think about what has happened in one galactic year. The last time the sun was at this point in its orbit, dinosaurs had not yet appeared. The supercontinent Pangaea was still forming. Life existed only in the oceans and was just beginning to colonize land. Since then, the sun has traveled once around the entire galaxy, carrying Earth and all its evolving life along for the ride. The sun has completed this circuit about 20 times since it formed, about 20 galactic years old. During our current galactic year, life on Earth has evolved from primitive land plants and early reptiles into the astonishing diversity we see today, including us. Entire ecosystems have risen and fallen. Continents have drifted, collided, split apart. Ice ages have come and gone. And through it all, the sun has been steadily moving along its orbit, passing through different regions of the galaxy, sometimes crossing spiral arms, sometimes drifting through the quieter spaces between. This raises an interesting question. Does our position in the galaxy affect life on Earth? Some researchers have suggested that passing through spiral arms might increase the rate of cosmic ray exposure or the likelihood of nearby supernovae, potentially triggering mass extinctions or ice ages. The evidence for this is mixed and controversial. What's clear is that Earth's environment is not isolated from the galaxy. We're part of a larger cosmic ecosystem, influenced by the slow dance of stars and gas around us. As the sun orbits, it also bobs up and down through the galactic plane, oscillating above and below the midline of the disk like a horse on a carousel. It crosses through the plane every 30 to 40 million years or so. Some researchers have looked for correlations between these crossings and events in Earth's geological record. But again, the evidence is ambiguous. What's not ambiguous is that space is not empty. Even in the regions between stars, there's material. The interstellar medium, a thin soup of gas and dust, pervades the entire galaxy. Most of it is hydrogen, some of it atomic, some of it molecular. There's also helium and traces of heavier elements, and tiny grains of dust, solid particles smaller than smoke particles, made of carbon, silicates, ices. These dust grains play a crucial role in the galaxy's ecology. They absorb and scatter light, particularly blue light, causing distant stars to appear redder than they actually are. They provide surfaces where chemical reactions can occur, where atoms can meet. They provide surfaces where chemical reactions can occur, where atoms can meet and bond in ways they couldn't in empty space. And they shield the interiors of molecular clouds from starlight, allowing temperatures to drop low enough for molecules to survive and star formation to proceed. The interstellar medium is not uniformly distributed. It's clumpy, organized into clouds of varying densities. Some regions are hot and diffuse, heated by supernovae or stellar winds. Others are cold and dense, the molecular clouds where stars form. Between these extremes, there are warm neutral regions, warm ionized regions, a complex multi-phase medium with different components at different temperatures and densities, all interacting, all exchanging matter and energy. Cosmic fields thread through this medium, influencing how gas moves and how stars form. These fields are weak compared to the magnets you encounter in daily life, but they extend over vast distances, and they channel charged particles, cosmic rays, high-energy protons and heavier nuclei accelerated to near light speed by supernova shocks or other violent events. Cosmic rays are a form of radiation that pervades the galaxy. They strike Earth's atmosphere constantly, producing showers of secondary particles that rain down to the surface. Most of them are harmless at ground level, but at high altitudes or in space, they pose a radiation hazard for astronauts. They also play a role in cloud formation on Earth and may have influenced the evolution of life in subtle ways. The galaxy is also filled with photons, particles of light, spanning the entire electromagnetic spectrum. Visible light, of course, the starlight we see, but also infrared, emitted by cool stars and dust clouds. Radio waves, produced by various processes including the spiraling of electrons in magnetic fields. X-rays and gamma rays, the highest energy photons, produced in the most violent environments, near black holes, in supernova remnants, in the jets of exotic objects called pulsars. Pulsars are the remnants of massive stars that exploded as supernovae, but left behind a core too massive to become a white dwarf, yet not massive enough to collapse into a black hole. These cores become neutron stars, objects about the size of a city, but containing more mass than the sun, so dense that a teaspoon of their material would weigh billions of tons. Neutron stars have immense magnetic fields, and they spin, sometimes hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles like lighthouses. If one of these beams sweeps across Earth, we detect it as a pulse, hence the name pulsar. The galaxy contains thousands of known pulsars, and probably many more that we haven't detected yet. They're cosmic clocks, their pulses so regular that they can be used for navigation, for testing fundamental physics, for detecting gravitational waves. When two neutron stars orbit each other, they gradually spiral inward, emitting gravitational waves, ripples in space-time itself. Eventually, they merge in a cataclysmic collision that produces both gravitational waves and a burst of light. Events so energetic, they forge elements heavier than iron, including gold and platinum. We detected the gravitational waves from such a merger in August 2017, and telescopes around the world swung into action, observing the event in every wavelength from gamma rays to radio waves. It was a triumph of astronomy, showing that we can now study the universe not just through light, but through space-time itself. Gravitational waves are a new way of sensing the cosmos, and they're revealing things that were hidden before. They allow us to detect collisions of black holes, mergers of neutron stars, possibly even echoes from the Big Bang itself. And they remind us that space is not a passive stage on which events occur. Space is dynamic, flexible, capable of being stretched and compressed, rippled and warped. Nowhere is this more evident than near the galactic center, near Sagittarius A, where space-time is severely distorted. Orbits near the black hole don't behave the way Newtonian physics would predict. They precess, their paths rotating slowly like a spirograph pattern, because space-time itself is curved. Light passing near the black hole is bent, gravitationally lensed, distorted into arcs and rings. Time itself runs slower there than it does out here, a consequence of general relativity, the theory that describes gravity as the curvature of space-time. If you could somehow survive near the black hole's event horizon, protected from the intense tidal forces, you would age more slowly than someone far away. Time would stretch. You could watch the universe outside speed up, stars racing through their life cycles, the galaxy evolving and fast forward. This is not science fiction. This is the universe we live in, where time is not absolute but relative, where it flows at different rates depending on gravity and motion. But let's step back from the extreme environment of the galactic center and consider the galaxy as a whole, as an ecosystem, as a system that sustains itself and evolves over cosmic time. The Milky Way is remarkably stable despite all the violence happening within it. Supernovae explode, stars collide, black holes consume matter, and yet the overall structure persists, maintained by the balance between gravity pulling inward and the motion of stars carrying them outward. This balance is not static but dynamic, like a river that maintains its shape even though the water is constantly flowing. The spiral arms persist even though the stars move through them. The disk maintains its flatness even though stars bob up and down through it. The galaxy is a pattern in motion, a structure carved not from solid matter, but from gravity and momentum and time. And embedded within this structure, in a quiet region between the major spiral arms, is our sun, an ordinary star, middle-aged, unremarkable in almost every way except one. Orbiting it is a planet where life emerged, evolved, and eventually became conscious, became capable of looking up and asking questions about the larger structure it inhabits. We are part of the Milky Way in the most fundamental sense, not just located in it, but made from it,
composed of atoms that were forged in its stars, shaped by processes that play out across its volume. Our existence is tied to the galaxy's history, to the supernovae that enriched the gas cloud from which the sun formed, to the stable environment that allowed complex chemistry to develop, to the relative safety of our position away from the violent galactic center and the busy spiral arms. There's a concept in astrobiology called the galactic habitable zone, the region of the galaxy where conditions are most favorable for life. Too close to the center, and the density of stars increases the risk of disruptive encounters, nearby supernovae, intense radiation. Too far out, and there aren't enough heavy elements to form rocky planets. The habitable zone is thought to be a ring somewhere in the middle regions of the disk, and we're right in it. But this doesn't mean life couldn't exist elsewhere. The universe is full of surprises. Organisms on Earth have been found in environments once thought too extreme for life, near volcanic vents at the bottom of the ocean, in Antarctic ice, in acidic hot springs, deep underground. Life is resilient, adaptable, persistent. It's entirely possible that life exists throughout the galaxy, perhaps in forms we wouldn't recognize, based on different chemistry, thriving in environments we'd consider hostile. The galaxy might be teeming with life, or we might be rare, perhaps even unique. We don't know yet. This is one of the
great open questions, and it makes looking at the Milky Way both humbling and exhilarating. Every star is a possibility. Every planet is a potential home. The galaxy is not just a physical structure, but a landscape of possibilities. To understand the galaxy better, astronomers have developed increasingly sophisticated tools. They observe in every wavelength, each one revealing different aspects of the galaxy's structure. Visible light shows us stars, the distribution of stellar populations, the glowing nebulae. Infrared penetrates dust, revealing star formation hidden inside molecular clouds, showing us the cool dust that pervades the disk. Radio waves trace the distribution of atomic and molecular gas, the raw material for future stars. X-rays highlight the hottest regions, supernova remnants, accreting black holes, the million-degree gas that fills parts of the galactic halo. One of the most important missions in recent years has been Gaia, a European Space Agency satellite that is measuring the positions, distances, and motions of more than 1 billion stars with extraordinary precision. Gaia is creating a 3-dimensional map of the galaxy, not just where stars are, but how they're moving, how fast, in what directions. This allows astronomers to reconstruct stellar orbits, to trace stars back to their birthplaces, to identify groups of stars that formed together and have since drifted apart. Gaia's data has revolutionized our understanding of the Milky Way's structure and history. It revealed stellar streams that were previously unknown. It showed that the disk has patterns in the motions of stars, ripples and waves that suggest the disk was disturbed by something, perhaps a dwarf galaxy passing through hundreds of millions of years ago. It provided evidence that the inner galaxy has a complex, multi-component structure, not the simple bulge that older models assumed. Before missions like Gaia, mapping the Milky Way was extremely difficult. We're inside the galaxy,
embedded in its disk, which means we can't see the overall structure directly the way we can with external galaxies. Dust blocks our view in many directions, particularly toward the galactic center. Distances to stars are hard to measure accurately, and without accurate distances, you can't build an accurate map. But technology has changed this. Gaia uses a technique called parallax, measuring the tiny apparent shift in a star's position as Earth orbits the Sun to calculate distances. The shifts are incredibly small, some less than a billionth of a degree, but Gaia can measure them. Combine this with data from other surveys, in other wavelengths, and a detailed picture emerges. We now know the shape of the Milky Way better than ever before, though there are still surprises and uncertainties. We know, for instance, that the disk has at least two main components: a thin disk where most star formation happens, and a thicker disk of older stars. We know the central bar is about 5,000 light-years long and oriented at an angle to our line of sight. We know the spiral arms have branches and spurs, complex substructures that reflect the turbulent processes of star formation. We know the dark matter halo is much larger than the visible galaxy, extending hundreds of thousands of light-years, maybe more. But there's still much we don't know. We don't know exactly how the spiral pattern formed, or why it's so persistent. We don't understand dark matter beyond its gravitational effects. We don't know how many stars the galaxy contains, or how many planets, or whether any of them harbor life. The Milky Way, despite being our home, remains in many ways mysterious. And that's part of its beauty. The fact that there are still questions, still discoveries to be made. Every generation of astronomers sees the galaxy a little differently, understands it a little better. The ancient Greeks imagined it as spilled milk. Medieval scholars thought it might be a vast congregation of stars. In the 1920s, Hubble proved that the Milky Way was just one galaxy among billions, shattering the idea that it was the entire universe. Today, we see it as a dynamic, evolving structure, a product of cosmic history, home to countless worlds. Let's drift for a moment among those worlds, the planets that orbit stars throughout the galaxy. We've discovered thousands of them now, exoplanets orbiting other stars, detected by the tiny dimming when they pass in front of their star, or by the tiny wobble they induce in their star's motion. These planets come in astonishing variety. Gas giants, larger than Jupiter, orbiting closer to their stars than Mercury orbits the Sun. Rocky super-Earths, planets with several times Earth's mass, but still solid surfaces. Ice giants, lava worlds, planets that orbit binary stars, planets in the habitable zones of their stars where liquid water could exist. Most of the exoplanets we've found are relatively close to us, within a few thousand light-years, simply because those are the easiest to detect. But extrapolating from these discoveries, astronomers estimate there might be as many planets in the galaxy as there are stars, perhaps more. Hundreds of billions of worlds, each with its own geology, its own atmosphere or lack thereof, its own history. Some of these planets orbit in the habitable zones of their stars, the region where temperatures allow liquid water to exist on a planet's surface. Water is essential for life as we know it,
a solvent that allows complex chemistry, a medium where molecules can interact and evolve. Finding a planet in the habitable zone doesn't mean it has life, but it means it could, at least in principle.
Earth itself has been habitable for billions of years, and life emerged relatively quickly after the planet cooled enough to have liquid water. This suggests that life might not require exceptionally rare conditions. It might be a natural consequence of chemistry when the right ingredients come together in the right environment. Or perhaps we're wrong about this. Perhaps life is extraordinarily rare, dependent on a chain of unlikely events that happened here, but almost nowhere else. This uncertainty makes every discovery exciting. Every new planet is a data point, helping us understand what's possible, what's common, what's rare. And the search continues, with new telescopes being built, new techniques being developed, each one capable of detecting smaller, more Earth-like planets, of analyzing their atmospheres, of searching for biosignatures, chemical signs that life might be present. Imagine a planet orbiting a star in the Perseus arm, 15,000 light-years away. If that planet has life, if that life has evolved intelligence, if those beings look up at their night sky, they would see the Milky Way from a different angle than we do. They would see different spiral arms dominating their sky. They would look toward the galactic center from a different direction, but they would see the same galaxy, the same structure, the same cosmic home. And if they had developed radio technology or powerful lasers, they might be sending signals into space, deliberately or inadvertently, signals that are right now washing past our solar system, undetected because we're not listening in the right direction or at the right frequency. Or perhaps they're listening, as we are, scanning the stars for any sign that they're not alone. The search for extraterrestrial intelligence, often abbreviated as SETI, has been ongoing for decades. Astronomers have pointed radio telescopes at promising stars, listening for signals that couldn't be produced by natural processes. So far, silence. Or rather, nothing that has been confirmed as artificial. The galaxy is noisy with natural radio sources, pulsars and magnetars and gas clouds, but no clear technological signature. This silence is sometimes called the Fermi paradox, after physicist Enrico Fermi, who supposedly asked, "Where is everybody?" If life is common, if intelligence emerges regularly, if technological civilizations develop, then where are they? Why haven't we detected them? Why haven't they visited us? The galaxy is ancient. There's been time for life to arise, evolve, spread, yet we see no evidence of anyone else. There are many possible explanations. Perhaps life is common, but intelligence is rare. Perhaps intelligence is common, but technological civilization is rare or short-lived. Perhaps civilizations destroy themselves before they can spread through the galaxy. Perhaps they're out there, but keeping quiet, for reasons we don't understand. Perhaps interstellar travel is simply too difficult, too expensive, not worth the effort. Perhaps we're looking in the wrong way, listening at the wrong frequencies, or they're communicating through channels we haven't imagined yet. Or, perhaps quietly, we are alone. Perhaps life on Earth, improbable and precious, is the only instance of biology in the entire galaxy.
This possibility is both terrifying and awe-inspiring. It would mean every living thing on Earth, from bacteria to whales to humans, carries a unique flame, a spark that exists nowhere else among the 100 billion stars. We don't know, and that uncertainty itself is significant. It means the galaxy remains a place of mystery, a landscape where discovery is still possible, where the most profound questions remain open. Let's return to the physical galaxy, to the matter and energy that compose it. We've talked about stars and planets, about black holes and spiral arms, but there's another component we should consider. The galaxy breathes, in a sense. It inhales and exhales matter on enormous timescales. Gas flows inward from the halo, pulled by gravity, feeding star formation in the disk. Stars form, live, die, and return much of their mass to space as stellar winds and supernova ejecta. But some of that energy is so violent that it drives gas outward, out of the disk into the halo. This creates a galactic fountain, a cycle where gas rises out of the disk, cools, and falls back down, enriched with heavy elements from the stars that processed it. There are also galactic winds, large-scale outflows driven by intense star formation or by activity near the galactic center. These winds can carry material out of the galaxy entirely, enriching the intergalactic medium, the thin gas that exists between galaxies. This means galaxies don't evolve in isolation. They exchange matter with their surroundings, with other galaxies in their group, with the cosmic web of matter that pervades the universe. The Milky Way is connected to Andromeda not just by gravity, but by this shared environment, the gas and plasma that fills the local group. In some sense, the boundary of a galaxy is fuzzy. There's the visible disk, the region dense with stars, but the dark matter halo extends much farther. The gravitational influence extends farther still, and the effects of a galaxy, through winds and radiation, can reach even beyond that. This interconnectedness is a theme throughout astrophysics. Nothing exists in isolation. Every star is influenced by the gas around it, by nearby stars, by the gravitational field of the galaxy. Every galaxy is shaped by its history of mergers, by its interactions with neighbors, by the cosmic environment in which it formed. And ultimately, everything is connected back to the beginning, to the Big Bang, to the moment when space and time and matter came into existence. The atoms in your body are as old as the universe itself. The hydrogen in your body, the protons in every hydrogen atom, were forged in the first few minutes after the Big Bang. Those protons have existed for 13.8 billion years, drifting through intergalactic space, falling into the proto-Milky Way, becoming a part of gas clouds, perhaps cycling through several generations of stars before finally ending up in the molecular cloud that collapsed to form the sun and planets. Every atom has a journey. The oxygen you're breathing right now was created in the core of a massive star somewhere in the galaxy billions of years ago. That star burned for millions of years, fusing hydrogen into helium, helium into carbon and oxygen, building up layers like an onion. When it finally exhausted its fuel, it exploded, scattering its enriched material into space.
That oxygen drifted through the galaxy, perhaps for hundreds of millions of years, before it became a part of the cloud that formed our solar system. Then it became a part of Earth, perhaps locked in rock, perhaps in the ocean, until eventually it was taken up by a living organism, cycled through ecosystems for billions of years, and finally inhaled by you. You are not separate from the galaxy. You are a pattern that the galaxy has created, a way that matter has organized itself into something capable of awareness. The iron in your blood, the calcium in your bones, the carbon in your cells, all of it is stardust, literally and precisely.
This realization can be overwhelming, or it can be comforting. It places you in a larger story, a narrative that spans billions of years and billions of light years. You are briefly conscious, briefly able to look up and understand before the atoms that make you return to the cycle, to the ongoing process of galactic evolution. Let's think about scale again, because it's easy to lose sight of just how vast the galaxy is. If you could shrink the Milky Way down so that the distance from the Sun to the nearest star, about 4 light years, was reduced to 1 centimeter, then the galaxy would be about 25 kilometers across. On this scale, the Sun would be invisible, smaller than a single atom. Earth would be unimaginably small. The solar system, out to the orbit of Neptune, would be about the size of a small coin. And yet, even at this reduced scale, traveling across the galaxy would be a significant journey. If you walked at a normal pace, it would take you days. If you drove, hours. And remember, we're talking about a scale where stars are centimeters apart, where the actual distances are so vast that light itself takes years to cross them. This is the arena in which cosmic events play out. Supernova shock waves expanding at thousands of kilometers per second take thousands of years to traverse a single light year. Spiral density waves move through the galaxy at tens of kilometers per second, but take hundreds of millions of years to complete one rotation. Gas clouds collapse over millions of years. Galaxies merge over billions of years. Human time is a brief flicker in this context. All of recorded history, from the first written records to today, spans only about 5,000 years. The Sun has moved about 1/50th of a degree along its galactic orbit during this time. If the galaxy were a clock, human civilization has existed for a fraction of a second. And yet, in that fraction of a second, we've gone from thinking Earth was the center of everything to understanding our place in a vast, ancient galaxy, one of billions of galaxies in an expanding universe. We've measured the distance to stars, mapped the galaxy's structure, detected planets around other suns, found gravitational waves from colliding black holes. The pace of discovery is staggering. What will we know in another 100 years? Another 1,000? What will we have discovered about the galaxy, about the universe, about the possibility of life elsewhere? These questions hover at the edge of now, tantalizing, pulling us forward. But for tonight, for this moment, it's enough to simply rest in the awareness that you're part of something much larger than yourself. The galaxy is your context, your environment on the grandest scale. Its history is your history. Its matter is your matter. Its story includes your story, however brief. There's something peaceful in this perspective. Your worries, your stresses, the difficulties of your day, they're real and they matter to you. But set against the backdrop of the galaxy, they're also temporary, small, part of the brief human experience within an incomprehensibly vast and ancient structure. This isn't meant to diminish your experience. It's meant to provide perspective, to remind you that you're connected to something grand and enduring. The galaxy will continue long after you. Stars will continue to form and die. The spiral arms will keep rotating. The slow collision with Andromeda will proceed. And in all of that continuity, there's a kind of comfort. Let's drift now through some of the stranger objects in the galaxy, the exotic remnants and unusual stars that populate the cosmic zoo. We've mentioned pulsars, those rapidly spinning neutron stars, but there are even more extreme versions called magnetars. These neutron stars have magnetic fields trillions of times stronger than Earth's, the strongest magnetic fields known in the universe. When a magnetar undergoes a starquake, a sudden cracking of its crust as it settles, it can release more energy in 1/10 of a second than the sun releases in 100,000 years, sending a burst of X-rays and gamma rays blazing across space. There are hypervelocity stars, objects moving so fast that they're escaping the galaxy entirely. Some of these stars were ejected by close encounters with the supermassive black hole at the galactic center. They fell inward in binary pairs. One star was captured by the black hole, while the other was flung outward at speeds of hundreds of kilometers per second, fast enough to overcome the galaxy's gravity and escape into intergalactic space. These stars are nomads, destined to drift alone through the void between galaxies, forever separated from the Milky Way. There are zombie stars, white dwarfs that should be dead, inert, but instead are accreting matter from a companion star, slowly building up mass until they reach a critical threshold and explode as Type 1a supernovae. These explosions are remarkably uniform in brightness, which makes them a useful standard candles for measuring cosmic distances, tools that helped astronomers discover that the universe's expansion is accelerating. There are stars orbiting each other so closely they almost touch, distorted into teardrop shapes by each other's gravity, exchanging mass, spiraling slowly inward until they'll eventually merge. There are stellar remnants called Black Widow pulsars, rapidly spinning neutron stars whose intense radiation is slowly evaporating their companion stars, consuming them like the arachnids they're named after. There are stars that don't behave the way theory predicts. Massive stars that should have exploded as supernovae, but instead seem to have collapsed directly into black holes, vanishing without the expected fireworks. Stars that vary in brightness in ways we don't fully understand. stars whose chemical compositions don't match anything we expect from standard stellar evolution. Each of these anomalies is a puzzle, a clue that our understanding is incomplete. And that's exciting, not frustrating. Science progresses through anomalies, through observations that don't fit expectations. Every strange object is an opportunity to learn, to refine our theories, to discover something new about how the universe works. The galaxy is also home to globular clusters, dense spherical swarms of hundreds of thousands of stars orbiting the Milky Way in the galactic halo. These clusters are ancient, among the oldest objects in the galaxy, formed early in its history. The stars within them are metal poor, confirming their age, and they're packed together much more densely than stars in the galactic disk. Near the center of a globular cluster, stars might be separated by only light days rather than light years. The night sky from a planet in such a cluster would be stunning, filled with thousands of bright stars. Globular clusters orbit the galaxy in elongated paths that take them high above and below the disk, then plunging back through it. They're like satellites, bound to the galaxy but not part of its main structure. There are about 150 known globular clusters orbiting the Milky Way, though some estimates suggest there might be more, hidden behind dust or
There are about 150 known globular clusters orbiting the Milky Way, though some estimates suggest there might be more, hidden behind dust or too faint to detect easily. These clusters pose interesting puzzles. Some of them show evidence of multiple generations of stars, which is strange for such old objects. They should have formed all at once and then stopped, with no new star formation because the cluster doesn't have enough gas to form new stars. Yet, the stellar populations in some clusters suggest otherwise, implying a more complex history. There are also open clusters, looser associations of stars in the galactic disk, much younger than globular clusters. These are groups of stars that formed together from the same molecular cloud and haven't yet drifted apart. The Pleiades, visible to the naked eye as a tight grouping of bright stars, is a famous example. These clusters gradually disperse over time as gravitational interactions with other stars and gas clouds pull them apart. But while they exist, they provide valuable laboratories for studying stellar evolution, because all the stars in a cluster are approximately the same age and composition. Our Sun probably formed in an open cluster about 4.5 billion years ago, along with hundreds or thousands of sibling stars. But those siblings have long since dispersed, scattered throughout the galaxy, and we have no idea where most of them are now. Some researchers are trying to identify solar siblings by analyzing the motions and compositions of stars, tracing orbits backward to see which stars were in the same place at the same time as the Sun formed. A few candidates have been found, stars that might have formed in the same cloud as the Sun, but confirmation is difficult. Imagine if we could identify a solar sibling and travel there. Would we find planets? Would those planets harbor life that shares a common origin with life on Earth?
seeded by material ejected during the solar system's chaotic early history? These are speculative questions, but they're fun to think about, and they remind us that the galaxy is full of connections we haven't yet traced. The galaxy also has structure on scales larger than individual stars or clusters. There are stellar populations with different distributions. Population 1 stars are young, metal-rich stars found in the disk and spiral arms. Population 2 stars are older and metal-poor, found in the halo and bulge. This division reflects the galaxy's evolution, with the oldest stars forming first when the galaxy had less heavy element enrichment, and younger stars forming later from gas that had been enriched by previous generations. There are also different kinematic groups, sets of stars with similar motions. Some of these groups are the remnants of dissolved clusters. Others are streams of stars following similar orbits, possibly captured from destroyed dwarf galaxies or ejected from the galactic center by some ancient event. The galaxy has thin disk, thick disk, stellar halo, each component with its own characteristic populations and motions. Understanding these components and how they relate to each other is key to reconstructing the galaxy's history, to understanding how it assembled and evolved over billions of years. And through all of this structure, through all these populations and components, there's the invisible scaffold of dark matter, holding everything together, providing the gravitational framework that shaped the galaxy's formation and maintains its current structure. Dark matter is perhaps the greatest mystery in modern astrophysics. We know it's there. We can measure its gravitational effects, but we don't know what it is. It's not ordinary matter, not protons and neutrons and electrons. It doesn't interact with light at all, which is why we can't see it. It might be composed of exotic particles predicted by theories beyond the standard model of particle physics, particles with names like WIMPs, weakly interacting massive particles, or axions. Or it might be something stranger, something we haven't imagined yet. Experiments around the world are searching for dark matter, trying to detect these particles directly or produce them in particle accelerators. So far, no confirmed detection, but the search continues, and every negative result narrows the possibilities, constraining what dark matter could be. Whatever it is, dark matter outweighs ordinary matter 5-to-1 in the universe as a whole, and its distribution shaped the formation of galaxies. The Milky Way's dark matter halo is essential to its structure. Without it, the galaxy would fly apart, the stars moving too fast for gravity alone from visible matter to hold them in orbit. This is actually how dark matter was first inferred. Astronomers measured the speeds of stars and gas at various distances from the galactic center and found that things were moving faster than they should be based on the visible mass. The rotation curve, a plot of orbital speed versus distance, stayed flat instead of declining as expected. This implied there was additional mass, invisible mass, extending far beyond the visible disk.
Similar observations in other galaxies confirmed the pattern. Dark matter seems to be a universal component of galaxies, an invisible majority that shapes everything we see, but remains frustratingly elusive. Let's shift perspective again and think about light, about the journey photons take through the galaxy. A photon emitted by a star travels outward in a straight line, or rather in a geodesic, the straightest possible path through curved space-time. Most photons never encounter anything. They just keep going, traveling through the galaxy, through intergalactic space, potentially forever. But some photons encounter obstacles. A dust grain might absorb a photon, warming slightly, then re-emit the energy as infrared light. A photon might scatter off an electron in a cloud of ionized gas, changing direction. A photon passing close to a massive object might be gravitationally lensed, its path bent by the curvature of space-time. The photons that reach your eye from a distant star have traveled for years, decades, centuries, sometimes thousands of years, without hitting anything, threading through the galaxy's vast emptiness. When you look at a star, you're seeing it as it was when that light began its journey, not as it is now. You're looking into the past, and the farther you look, the further back in time you see. The nearest stars are seen as they were a few years ago. Stars in the galactic bulge are seen as they were tens of thousands of years ago. The center of the galaxy, 26,000 light-years away, is seen as it was 26,000 years ago, during the last ice age on Earth, when mammoths still roamed and humans were hunter-gatherers. This light travel time means we can never see the galaxy as it is now, all at once. We see a patchwork of different times, a composite image where nearby objects are recent and distant objects are ancient. If the galaxy
has some central coordinating signal, some way of synchronizing events, we have no way to know about it. Causality is limited by the speed of light. Events can only influence each other if there's been time for light to travel between them. This makes the galaxy, in a sense, a collection of isolated regions that can't coordinate, can't respond to each other in real time. The supermassive black hole at the center doesn't know what's happening in the outer spiral arms, and won't for thousands of years. The galaxy is not a unified entity, but a loose collection of parts, each evolving according to local conditions, linked only by gravity and the slow exchange of matter and energy. Yet, despite this lack of coordination, patterns emerge. The spiral arms form and persist. Star formation regulates itself through feedback mechanisms. The galaxy maintains a rough equilibrium between inflows and outflows, between star formation and stellar death. Order arises from local interactions, without any central control, a theme common in complex systems throughout nature. As you lie here, letting these thoughts drift through your mind, consider that you're connected to all of this through bonds of matter and energy and history. The light you saw today from the sun began as energy in the sun's core, where hydrogen fuses into helium. It took thousands of years for that energy to random walk its way from the core to the surface, bouncing from atom to atom, gradually cooling, transforming from high-energy gamma rays into visible light. Then it crossed space in 8 minutes and entered your eye, triggering chemical reactions in your retina, sending signals to your brain, creating the sensation of light. That's a journey spanning space and time, connecting you directly to the nuclear furnace at the heart of the solar system, which itself is connected to the broader galaxy through gravity and motion and shared history. Everything is connected, on time scales and distance scales that dwarf human experience, but nevertheless included. The galaxy is not just a place, it's a process, an ongoing event, a story being written in stars and gas and gravity. And you're part of that story, a brief chapter, a few lines in an epic so long that most of it will never be read, never be remembered. But it's real, and it's happening. And right now, in this moment, you're here to witness a tiny piece of it. Let your breathing slow even more now. Feel the weight of your body against the surface beneath you. The galaxy continues its slow rotation, indifferent to your presence, vast beyond comprehension. But you're here, aware of it, able to think about it, able to feel wonder at the sheer scale and beauty of it all. In about 4 billion years, the Milky Way and Andromeda will begin their collision. It will be spectacular, though not in the way collisions usually are. Galaxies are so much empty space that when they interpenetrate, almost no stars actually hit each other. Instead, their gravity will distort each other's shape, pulling out long tidal tails of stars, triggering massive bursts of star formation as gas clouds collide and compress. The two galaxies will pass through each other, then fall back together, pass through again, slowly losing orbital energy, settling gradually into a single, larger galaxy. The process will take billions of years, and by the time it's complete, the solar system, if it still exists, will be in a very different location, perhaps flung into the outer halo, perhaps closer to the new galaxy's center. But that's so far in the future that it's almost meaningless to worry about. By then, the sun will be near the end of its life, swelling into a red giant, possibly engulfing Earth, or at least scorching it lifeless. The details are uncertain, but the end point is clear. The sun, like every star, has a limited lifetime. This impermanence is true of everything. Stars, galaxies, planets, life, all of it temporary on cosmic scales. But temporary doesn't mean meaningless. A sunset is temporary, but beautiful. A song is temporary, but moving. Your life is temporary, a few decades at most, but it's yours, filled with experiences and connections, and moments of joy or peace or wonder. The galaxy will outlast you, yes. It will outlast humanity, outlast Earth, outlast the sun. But right now, in this brief moment, you're part of it. You're experiencing it. And that's enough. Let's return once more to the idea of home. Because that's what the galaxy is, ultimately. Not just Earth, not just the solar system, but this entire vast structure, this spiral of stars and gas and mystery. You've never left it. You never will. Every journey you've taken, every place you've been, has been within the Milky Way. Even if humanity eventually travels to other stars, colonizes other planets, spreads through the galaxy, we'll still be home, still within the bounds of our native galaxy. There's something comforting in that, a sense of belonging that transcends the everyday. You belong here, not just in your room or your town or your country, but here in this galaxy, this particular arrangement of matter and energy, this island of stars in the cosmic ocean. And the Milky Way itself belongs to the local group, which belongs to the Virgo supercluster, which belongs to the larger cosmic web, filaments and walls and voids stretching across the observable universe. Everything is nested within everything else, layers of structure on ever larger scales, until finally you reach the edge of what we can observe, the cosmic horizon beyond which light hasn't had time to reach us yet. But you don't need to think about those scales right now. The galaxy is vast enough, beautiful enough, mysterious enough to occupy your thoughts as you drift towards sleep. Let your mind wander through spiral arms, past glowing nebulae, through dark molecular clouds where stars are being born. Imagine the view from a planet orbiting a star in the galaxy's bulge, where the night sky blazes with light. Imagine a rogue planet, ejected from its solar system, drifting alone through interstellar space, dark and cold and silent, a refugee from some ancient gravitational chaos. All of these places exist right now as you lie here. They're part of the same galaxy, the same structure, connected by gravity and history, even if they'll never interact directly. The galaxy contains multitudes, every possible stellar environment, from dense clusters to lonely halo stars, from the violent core to the peaceful outskirts. And somewhere in all that vastness, there might be others, other beings, other consciousnesses, other species looking up at their own sky and wondering if they're alone. We don't know. Maybe we'll find out someday. Maybe we never will. But the possibility exists, and that alone is worth contemplating. What would you say to them, if you could? If there was a way to send a message across thousands of light years, what would you want to communicate? Your existence, probably. The fact that you're here, that you're aware, that you're part of the galaxy too. Maybe you'd describe Earth, the blue planet with its oceans and continents and diversity of life. Maybe you'd try to convey something about human culture, our art and music and science and stories. Or maybe you'd say something simpler. Hello. We're here. We see you. You're not alone, and neither are we. That message would travel at the speed of light, taking years or centuries or millennia to arrive, and by the time any reply came back, you'd be long gone.
That message would travel at the speed of light, taking years or centuries or millennia to arrive, and by the time any reply came back, you'd be long gone. But the message would persist, a sign that once, on a small planet orbiting in the ordinary star in the outer regions of the Milky Way, there was someone who cared enough to reach out, to try to make contact, to bridge the vast distances between stars. That's a hopeful thought, a gentle thought to carry into sleep. The idea that connection is possible, even across cosmic distances, that despite all the vastness and emptiness, there might be threads linking conscious beings throughout the galaxy, threads of curiosity and hope and wonder.
Or perhaps you're content not knowing, content to rest in the mystery, to let the galaxy remain partially unknown, partially unexplored. There's beauty in mystery, in questions without answers, in the sense that there's always more to discover, always further to go. The galaxy has been here for billions of years before you, and it will remain for billions of years after you're gone. Your life is a brief moment within its vast span, a single breath in a symphony that's been playing since long before stars like the sun existed. But that brief moment is yours. It's real. It matters. You've spent this time tonight traveling through the galaxy in your mind, visiting places you'll never physically go, imagining structures too large to see all at once, connecting yourself to the larger cosmic story. And now, as this journey draws toward its close, you can let go of the details, let go of the facts and figures, and simply rest in the feeling that comes from knowing your place in the universe. You're small, yes, but you're part of something immense. You're temporary, but you're connected to processes that span billions of years. You're isolated on a single planet, but that planet is embedded in a galaxy filled with wonders, a structure of unimaginable beauty and complexity. The Milky Way is always there, turning slowly, indifferent but not hostile, vast but not empty. It's your context, your home on the largest scale. And tonight, you visited it, explored it with your mind, traced its structure and history and mystery. Now, let it cradle you as you drift toward sleep. Let the thought of those spiral arms wrapping around you be a comfort, a reminder that you're held within something ancient and enduring. Let the stars watch over you, billions of distant suns, each one a light in the darkness, each one a possibility. Your breathing has slowed. Your thoughts are becoming softer, less focused, beginning to dissolve into the patterns that precede dreams. This is natural. Welcome. You don't need to hold on to anything now. You don't need to remember or understand or analyze. Just let yourself drift. The galaxy continues without your attention. It doesn't need you to observe it or think about it. It simply is, vast and patient, turning through the darkness of space, creating and destroying and transforming, following the laws of physics that govern all things. And you, briefly conscious within it, can now release that consciousness into rest, can let go of the day, the thoughts, the journey through stars and gas and time, can simply be for a moment before sleep takes you completely. The Milky Way holds billions of worlds, billions of stories, billions of moments of wonder and beauty and change. You've touched a few of them tonight, skimmed the surface of an ocean too deep to fully explore, but that's enough. You don't need to know everything. You just need to rest, to let the knowledge that you've gained tonight settle into your mind like sediment, drifting down through still water. Tomorrow, the galaxy will still be there. The stars will still shine. The spiral arms will still rotate, and you'll be part of it, continuing your own journey through time and space, moving along the sun's orbit, carried through the galaxy at hundreds of kilometers per second, participating in the great cosmic dance, whether you're aware of it or not. But for now, for this moment at the end of your day, you can simply rest.
You can let the weight of consciousness lift. You can trust that the universe will continue without your effort, that the galaxy will take care of itself, that you can safely let go and drift into sleep. The Milky Way, the river of stars, flows on. It has always flown. It will always flow, at least for billions of years, until the far future when the collision with Andromeda reshapes it. And even then, the stars will persist, the matter will persist. The ongoing process of existence will continue in new forms. You're part of that flow. You always have been. You always will be, at least in the sense that the atoms that make you will persist, will return to the cosmic cycle, will perhaps someday be part of new stars, new planets, new forms of matter and structure. That's the ultimate recycling, the ultimate continuity. Nothing is truly lost. Everything transforms. The galaxy is a great engine of transformation, turning simple hydrogen into complex elements, turning gas clouds into stars and planets, turning matter and energy into structure and complexity, and occasionally into life and consciousness. You're a wave in that process, a pattern that has briefly formed and will eventually dissolve. But while you exist, you're real, you're significant, you matter, at least to yourself, at least to those around you, at least in this moment. And that's enough. That's always been enough. Let your last thoughts tonight be of starlight, of the gentle glow of distant suns, of the darkness between stars that's not empty, but full of potential, pregnant with the possibility of future formation and change. Let yourself feel the slow rotation of the galaxy, the patient turn of eons, the timeless rhythm that underlies all temporary things. You're safe here. You're home. The galaxy cradles you. The earth supports you. The air sustains you. You can release your grip on wakefulness now. You can surrender to sleep, knowing that when you wake, the journey will continue. Your own personal orbit through time and space. Your own small but real contribution to the galaxy's ongoing story. The Milky Way spins in darkness and light, a spiral of ancient fires and unborn possibilities, a structure that contains all human history and extends far beyond it. A home you never leave, even as you dream of distant stars. Rest now. The galaxy will be here tomorrow. The stars will wait. The mystery will remain patient and vast, ready for you to return when you're ready, but requiring nothing of you now except that you let go, that you drift, that you allow sleep to carry you away from these thoughts and into the quiet darkness where dreams begin. The river of stars flows on, and you flow with it, a brief sparkle of consciousness in an ocean of matter and energy and time. Beautiful, temporary, real. Good night, traveler. The galaxy watches over you, indifferent but present, vast but intimate, eternal but full of change. You're part of it all, now and always, a thought in the mind of the cosmos, a pattern in the great spiral of being. Good night. If you're still awake, you can drift into the next chapter or let sleep take you into dreams of stars.